Hi, and welcome to another video in fluid mechanics. Up until this point, we have dealt primarily with enclosed flows. These are flows that have boundaries on all sides and include both channels and pipes. In analysis of these flows, we have come to solve the velocity field, u, v, and w, and also learned a bit about the pressure field as well. We studied these flows in both laminar and turbulent states. Today, we move on to the world of external flows. Unlike enclosed flows, these flows can be open and extend effectively into infinity in at least one direction. Specifically, we'll be interested in boundary layers, the layer of velocity gradient near the surface due to viscosity acting on the fluid, and the no-slip condition at the wall. Like with enclosed flows, we will try and solve for the velocity field and the pressure field. Today, our focus will be on laminar boundary layers, and we'll save turbulent boundary layers for the next video. Let's jump right in. External flows are our next focus. These flows are open on one or more sides and often exhibit growth or development in the streamwise direction, leading to more complicated flows than we saw with enclosed flows. These types of flows include boundary layers, a velocity gradient near a solid surface, also jets, a concentration of moving air, wakes, which is a velocity deficit region that's often unsteady and downstream of a body moving in a fluid, and shear layers, where two flows with different velocity come together. All these types of flows exist in the world of fluid mechanics and warrant specific analysis. Today, our aim is to better understand the laminar boundary layer. Consider a plate moving in a fluid or a fluid passing by a solid plate. There is some free stream velocity, u infinity. Near the wall, we have what's called the no-slip boundary condition. Physically, this means velocity super close to the wall has to have the velocity of the wall itself due to friction. So u at y equals 0 is 0. Now, we know far from the wall the velocity field does not feel the pressure of the wall, so the velocity field remains u infinity, which is the free stream velocity. In our fluid, there must be a continuous region where the fluid changes from the zero velocity at the wall to the free stream velocity far from the wall. This region is called the boundary layer, and it grows as flow moves downstream. Boundary layers are essentially molecular diffusion, which is viscosity, creeping out slowly further and further from the wall. In these layers, viscosity is deemed to be important due to the meaningful vertical velocity gradients. These layers are generally quite small relative to the surface moving through the fluid, but despite their small size, they are absolutely critical in understanding how fluid forcing works on external vehicles and aerodynamics, heat transfer, and even atmospheric flows. Our goal is to be able to describe how a boundary layer grows downstream, what the thickness is, what the velocity profile looks like, and how that imparts a force on a surface. As we did with all of our flows, let's see how far we can get with theory using just the conservation equations. Let's set up our flow with a schematic of a boundary layer. We have a free stream velocity coming in, u infinity. The dashed white line is the line that represents the upper bound of the boundary layer. We can mark our u equals 0 wall condition, and that's it. Notice that here the flow goes past the surface. Remember, this still applies to moving vehicles. We have just attached our coordinate system to the vehicle itself. To start analysis, we're going to need some assumptions. Here we will use some familiar assumptions and some newer ones midway through our analysis. First, our fluid is incompressible, so density is a constant. Second, the fluid is steady, which means nothing changes in time in our flow. We also assume it's two-dimensional and two-component, so nothing substantial happens in the out-of-plane direction. Remember, the steady and the 2D 2C assumptions are very common for laminar flows. At this point, we almost instinctively write fully developed, but for boundary layers and most external flows, this is not the case. These flows develop in the x direction, and we can no longer ignore x gradients in the velocity field. So regrettably, we have to leave this assumption behind because we can't use it. Last, let's assume there are no body forces for now. After assumptions, which help us simplify our equations, we will need boundary conditions, which we need to solve the equations. At the wall, we have the no slip and no penetration conditions, meaning the streamwise and vertical velocities are 0 where they meet the surface. These are specifically wall conditions. However, now that our fluid is unbound in the positive y direction, we have some new conditions we can utilize as it goes off into infinity. We take the limits on the flow behavior as y approaches infinity, or gets so far from the wall it no longer feels the wall. As y goes to infinity, the streamwise velocity becomes the free stream velocity, u infinity. As a result, the free stream is an idealized location where there is no vertical velocity, so we set v to be 0. Lastly, we also just say there is no pressure gradient in the free stream direction as y goes to infinity, as the free stream is just a constant x velocity. This condition on the pressure gradient will be critical in being able to deal with the pressure terms later on. As always, we make our start with the conservation of mass for an incompressible fluid. We can only remove the term dw dz due to the assumption that the flow is two-dimensional. And that's as far as we can get. We can't say anything about the v velocity as we would for the enclosed flows because we have two gradients here to keep track of. So, we move right on to our conservation of momentum in the x direction to see what that tells us. Let's write them out in their entirety. The material derivative representing flow acceleration is on the left, then that is balanced by the forces of pressure, viscosity, and a body force on the right. To simplify, let's apply our assumptions. We're going to be able to remove four terms here, the du dt term because the flow is steady, both the derivatives in the z direction because the flow is two-dimensional, and the body force term. And what we're left with is a rather intimidating balance of momentum terms, pressure, and viscosity terms. Let's call this equation 1. If we did the same process on the conservation of momentum in the y direction and applied our assumptions, we would find a similar result here. These two equations are really hard to work with in the current state. In order to move forward, we need to be able to do something else to make them more simple. So, we're going to make some observational assumptions that are based on observations we've made for this type of flow in the past. Let's consider the growth characteristics of the boundary layer, and maybe we can say something about the sizes of some terms compared to others. In the beginning of the boundary layer development, growth is rapid. However, not long into development, the growth gets dramatically more gradual. The bulk of the flow is gradual growth, so let's claim that in our analysis we're considering only this gradual growth region. This leads us to some more possible assumptions. Because growth is slow in the x direction, we claim that the velocity field changes in the wall normal direction y are much larger than changes in the streamwise direction x. Remember, vertically the boundary layer is small, so things have to change rapidly to go from 0 velocity to the free stream velocity in the y direction. This means that if we ever see these two terms together in an equation, for example du dy versus du dx, we assume one dominates the other, the du dy term, and we remove the smallest term, du dx. Keep in mind here you can only compare like terms, meaning only u terms compared to u terms and v terms compared to v terms. For example, we can't compare du dx and dv dy. Next, we're going to assume that the streamwise velocity is much larger than other velocity components, which is typically a fine claim for these flows since the majority of the flow is in the streamwise direction. Soon, we will be comparing terms and deciding which to get rid of based on size. So let's sort the terms into whether they are considered to be big, small, or tiny. U and y derivatives of the u velocity are the biggest. Next up, we have v and y derivatives on v, as well as the streamwise derivatives on u. These are small, but not too small. Last, we have the tiny terms, streamwise gradients of v. We can organize these like this because of generally how we've observed boundary layers to behave. Now, we can write both conservation of momentum equations we have, equations 1 and 2, and label each term with their size. In equation 1, we have some terms that are big times the small, and some that are just small, and some that are just big. Let's keep the big and the big times small terms. We remove only the smallest term in the equation. In equation 2, we have some tiny terms now. We keep everything that is small, or a big times a tiny term. We can remove the smallest term, which is just tiny. Notice this is the same term we removed above. Now, if we compare equation 1 to equation 2, term by term, we notice that all terms in equation 1 are much bigger than their partner term in equation 2. And we don't know anything about the pressure terms. However, if we know all the terms in equation 1 are much greater than equation 2, we also know that the pressure gradient in 1 is bigger than the pressure gradient in 2. This is important. If we say dP dx is much bigger than dP dy, then we know that p is not a function of y and that it is approximately only a possible function of x. So, p is a constant in y. And if we pair this with our boundary condition on the pressure gradient, which says as y goes to infinity, the pressure gradient goes to 0, this means the pressure gradient is 0 everywhere because it's a constant in y. Essentially, through this deduction, we can ignore the streamwise pressure gradient. This brings us to our final form of the conservation equations for a laminar boundary layer. They're still rather complicated, but they're totally solvable numerically. Back in 1908, these were originally derived and solved by Prandtl and his student Blasius, a famous pair of researchers who pioneered boundary layer research. Their solutions led to the following discretized form of the boundary layer shape. Here's a table showing their results. The left column is effectively the y-coordinate. The profile is self-similar in x, meaning it doesn't change shape in x, it just grows. This is why we see the x variable come into the y column, because the x variable is acting to stretch the vertical coordinate. Next to this is the velocity normalized by the free stream, so it goes to 1 far from the wall. If you plotted this data, it would represent the shape of a laminar boundary layer. These equations, and a ton of analysis in boundary layers, require the Reynolds number. For boundary layers, the Reynolds number is the product of density, the free stream velocity, which acts as our velocity scale, and the x location of interest, which is sometimes our length scale, all divided by the viscosity. The Reynolds number tells us when flows transition to turbulence. For smooth flat plate flows, this is estimated to be around 500,000. Now that we know the boundary layer shape, let's determine how we can discuss its size. We measure the boundary layer height with 3 main strategies depending on our needs. First, the most simple strategy is to define a physical distance above the surface and mark its height. This is called the disturbance thickness delta, and is the y location where the velocity in the profile is equal to 99% of the free stream velocity. Sometimes people use 95% instead of 99%, but regardless, it's the same procedure. People use this because it's simple and easy to find and measure. The second strategy is called the displacement thickness. Consider the boundary layer. The velocity deficit is the region in purple where the flow velocity is less than the free stream velocity. This space has an area, which we're going to call area A. We can equate this area A to a rectangle that has one length as the free stream velocity, which is known, and some height, which is the displacement thickness, which we're trying to find. Physically, interpret this as the height from the ground that the surface would have to extend in order to push the fluid back into being uniform. It's a bit harder to calculate and requires the integral of the velocity profile. People use this in aircraft design where they consider this delta star as part of the surface and ignore viscosity above this distance. Lastly, we have the most complex way to define the height, the momentum thickness. Similar to the displacement thickness, we consider the area beneath velocity profile, but instead we're considering the momentum deficit, so u squared, and not the velocity deficit. This means if we found a rectangle with an area A equal to the momentum deficit, the length of the rectangle is u infinity squared, which is known, and the height of the rectangle is our theta, the momentum thickness. The calculation is similar and also needs an integral. This is generally used when considering the surface drag, because the momentum deficit is more heavily connected to drag force than just velocity. For laminar flows, we already have the solution numerically, and we can exactly define the behavior of these three thicknesses as they vary in the streamwise direction, and they're all functions of the local Reynolds number. As you can see, the boundary layer grows downstream non-linearly because x appears in the square root of the Reynolds number. So now we have a good handle on the boundary layer size, shape, and growth. In aerodynamics and in industry, we're generally interested in the force the fluid applies on the moving surface. Boundary layers have a wall shear, and the wall shear results in a shear stress which makes a drag force. Recall Newton's law of viscosity. If we calculate it at the wall, we have the shear stress at the wall. Numerically, we can do this derivative to our flow field and come up with another estimated expression for laminar boundary layers. Interestingly, you might notice that the further downstream you go, the less the fluid pulls on the surface. This is because as the boundary layer grows, the velocity gradient near the wall gets smaller. This is popularly represented in non-dimensional form, where a form of the flow inertia, 1/2 rho u squared, is used to normalize this stress. This is the skin friction coefficient, C sub f, and it defines the behavior for the wall skin frictions relative to the flow inertia. Much like Reynolds number, this is similar to viscosity versus inertia. It's important to keep in mind the skin friction coefficient is different from a drag coefficient. The skin friction coefficient is just used to non-dimensionalize the wall shear. You cannot get drag from it directly. However, we can turn the shear stress due to friction into a drag force. It's important to point out that because our shear stress is now a function of x, we can no longer use the shortcut that total wall forcing is just the shear stress times the wall area. We have to move to the general definition where the force is the integral of tau over an area. Let's assume flow is uniform in the z direction and give the plate a width w. By assuming it's uniform, w can come out of the integral. We integrate from 0 to L, which is the plate length, over dx. The final expression tells us the wall force is a function of the velocity, plate length, and the Reynolds number based on the length. It's important to note that for boundary layers, when there is a subscript on the Reynolds number, it's typically referring to the length scale you use in the Reynolds number calculation. Sometimes you'll see Re sub L, or Re sub X, or even Re sub theta, which is a Reynolds number based on the momentum thickness. This drag force can also be non-dimensionalized using the flow inertia. The general drag coefficient is the force of drag divided by the area of the surface times 1/2 density times velocity squared. Specifically for laminar boundary layers, this transforms into the following function of Reynolds number based on plate length. And that's it for the equations. These equations are valuable to keep in your tool belt when analyzing boundary layers because even when flow is turbulent, we need to use these to calculate the laminar portion of the plate, as we'll see in the next video. In practice, you will certainly come across boundary layers in some way, shape, or form. In aerodynamics, they are the direct cause of lift and drag on aircraft wings. The growth of the boundary layer leads to a phenomena called separation, which can dramatically change the forces a body feels due to a fluid. Last, boundary layer analysis is the root of climate modeling, trying to predict flow patterns on the planet. So understanding what a boundary layer is and how to work with it is critical. And that's it. Let's review. Today we introduce laminar boundary layers, a specific external flow that is a region of lower velocity fluid that grows on an external surface in a flow field due to viscosity. We used our typical theoretical approach to understanding a flow with some unique assumptions and boundary conditions. In the end of our analysis, using some creative assumptions and comparing the size of different terms in our equations, we were able to arrive at a solvable set of equations that define the velocity. Prandtl and Blasius solved these equations to get the self-similar shape of the laminar boundary layer known as the velocity profile. The boundary layer height was quantified using three separate methods: the disturbance thickness, the displacement thickness, and the momentum thickness. We then used the velocity field to calculate the stress that acts on the surface and the resulting drag force on the plate due to the fluid. While laminar boundary layers are typically overshadowed by turbulent boundary layers, they are still a critical aspect of fluid mechanics and analysis. I hope you enjoyed the video, and thanks for watching.